Good morning, everyone. This is Julie McDonald with Microcom Technologies, and I'd like to thank all of you for attending today's webinar with MetaGeek. Today's host is Joel Crane, technical trainer, and he'll be presenting today. And if anyone has any questions, please feel free to submit them in the question box, and Joel will answer them at the end of today's presentation. Joel, thank you much for being here with us today. I am finished for now, and you can take it over.
Great, thanks, Julie. Welcome to Small Business Wi-Fi with Insider Office and WiSpy. In this webinar, I'm going to show you how to use Insider Office and WiSpy to troubleshoot and optimize a small business Wi-Fi deployment. This could be a smaller network, somewhere between maybe 3 and 20 access points, so kind of a smaller size network. Maybe you'd find a network like this in an office environment or a small business environment, maybe even in a warehouse or even in a large home that has a lot of home automation type equipment going on. So you could use this for several different types of networks. And just so you know a little bit about me, like Julie said, my name is Joel, and I'm the technical trainer here at MetaGeek. We're a small company based out of Boise, Idaho, and we make easy-to-use wireless troubleshooting tools. That includes both hardware and software. Our three main product lines for software are Insider Office, which we'll talk about today, as well as Channelizer, which is our enterprise-grade spectrum analysis tool, and then IEPA, which is our enterprise-grade packet analysis tool. And both Channelizer and Insider Office rely on the WiSpy, which is a small USB spectrum analyzer that you can use to gather spectrum analysis data. And those are made right here in Idaho with real 100% Idaho grown potatoes. Just so you know a little bit about what we're going to talk about today, the first thing I'm going to do is I'm going to go over some Wi-Fi fundamentals. There's some things that you have to understand in Wi-Fi to really grasp how to use Insider Office and the WiSpy to deploy and troubleshoot your wireless network. We'll go through a few things like the differences between 2.4 and 5 gigahertz. We'll talk about the half duplex nature of Wi-Fi. We'll talk about non-Wi-Fi interference and the effects that it can have on Wi-Fi. And then we'll talk about the different types of interference that you'll encounter with Wi-Fi. After that, we'll jump into some specifics, some things that are really specific to this application, such as channel planning, how to achieve good wireless coverage and how to measure coverage. And then we'll also talk about security a little bit. In part 2 of this webinar, as we transition into part 2, we're going to jump into a live demo with Insider Office and the WiSpy. Here's a picture of what the WiSpy looks like. This is the WiSpy DBX. That's our dual band model that does both 2.4 and 5 gigahertz. We'll use those tools to do a few common tasks like avoid non-Wi-Fi interference. We'll also use it to measure and avoid any congested channels, any channels that have a lot of Wi-Fi congestion on them. And then we'll talk about how to use them for channel planning, checking coverage, performing security checks, and then at the end we'll run through a network checklist that you can use to make sure that your network is ready to go using Insider Office and the WiSpy. So the first thing I want to talk about is the half duplex nature of Wi-Fi, and I talk about this in pretty much every webinar that I give because it's the most important thing that you can understand about Wi-Fi. This is the building block. This is the core concept that you have to know. It's kind of like algebra in that you have to start with the basics and work your way up in Wi-Fi. So the first thing I want to talk about is this half duplex nature of Wi-Fi. Now, many of us are familiar with Ethernet, and if you've ever stripped back an Ethernet cable to see what it looks like, inside the Ethernet cable, you'll notice that there are multiple twisted pairs of copper inside the cable. And what that allows us to do is it allows us to achieve full duplex connectivity. With full duplex connectivity, we can send traffic in 2 directions at the same time. It's kind of like a 2-lane highway. With a 2-lane highway, we can send traffic east and west simultaneously. That's basically a full duplex highway. But if we limited ourselves to half duplex, we would only be able to send traffic in one direction at a time. Half duplex Wi-Fi is kind of like human conversation. When you're talking to a friend, only one of you can talk at a time. If you say something and if your friend says something at the exact same time, you can't understand each other. You basically interrupt each other because you can't talk and listen at the exact same time. Wi-Fi is the exact same way. Only one Wi-Fi device can talk on a channel at a time. If we have an access point and it transmits at the same time as a client device like this laptop, if they both transmit at the same time, they're just going to cancel each other out and they're not going to be able to understand each other. Only one device can talk at a time. So what does a wireless conversation typically look like? Well, let's go through the process to see how devices talk, how they figure out how they coordinate and how they talk. So let's say that we have a wireless access point here. We've got our AP here, and it needs to transmit some data over to this laptop. So the first thing that the AP is going to do is it's going to perform a cleared channel assessment. It's going to listen to the channel and see if anything is talking. And if nothing is talking, it'll go ahead and use that opportunity to transmit its data over to the laptop. Now the laptop is going to receive that data and it's going to pull out the magnifying glass. It's going to take a look at that data because it wants to make sure that it understood the data. And if it understood that data, it'll go, yep, check, I understood the data, and it will reply with an acknowledgement, or just an ACK for short, to say, yep, I received the data, and that lets the router know that it received the data. Now there's a couple of things that can go wrong here. Let's say that the access point transmits the data, but something else starts transmitting at the exact same time and interrupts that conversation. When that happens, it will corrupt the data. So now by the time the data gets to the laptop, it's corrupt. Or maybe the laptop is just a little bit too far away from the access point. Maybe by the time the signal gets there, it's just really kind of weak, and so the laptop just can't understand what the access point's trying to say. The data is too garbled. When that happens, the laptop will not send an acknowledgement. It won't be able to understand that data, so it will not send an acknowledgement. And when that happens, the access point's going to notice, okay, well, I never received an acknowledgement from the client device, so it must not have received the data frame. So it will retransmit that data, and it will retransmit that data as many times as it needs, within some certain limitations. It will transmit that data until finally some of that data makes it through and the laptop can reply with that acknowledgement to say, yep, check, I received the data. I like to think of Wi-Fi as a lot like my 2-year-old daughter in this way. I have a daughter that's 2. In fact, I have 3 daughters, but the youngest is 2. And she about, I don't know, maybe 4 months ago started talking a lot. You know how that is. If you've been around kids, you know exactly what I'm talking about. If I'm sitting on the couch and I'm reading a book or maybe watching a show on TV or something like that, you know, if I'm engrossed in something and she asks me a question, if I don't give her some kind of acknowledgement, she will just repeat herself over and over and over and over and over again. And she will continually repeat herself until finally I give her some kind of acknowledgement. So if you've ever had kids, or if you've ever been around kids, or maybe you've just seen some kids from a distance, you know that kids are a lot like Wi-Fi in this way. They will repeat themselves continually until you give them some kind of acknowledgement. So what happens when we have more than one access point and more than one client device on a channel? Well, in this scenario, it's still half duplex, and we can still only have one device talking at a time. If we've got an Android phone here, and let's say that this Android phone is transmitting some data to this access point, while that data transmission is occurring, all the other devices on the channel in range have to be quiet and wait for their turn to talk. On any given channel at any given time, only one device can talk at a time. Only one device. And that includes neighboring devices as well. It doesn't matter if it's another access point that's part of the same network. It doesn't matter if it's a neighbor with a completely different network. If it's on the same channel, they all have to take turns talking. One device talks on a channel at a time. Non-Wi-Fi interference is a big deal here as well. In the 2.4 gigahertz band especially, there's lots and lots of non-Wi-Fi devices that also use that same slice of spectrum. They also use the same frequency bands. A notorious one is the good old microwave oven. And not to freak you out or anything, but microwaves cook food by bombarding it with 2.4 gigahertz. Now, don't worry, they've got a bunch of shielding to help contain all of that. When it's not radioactive or anything like that. It's completely different. But they cook food by bombarding it with 2.4 gigahertz, and that excites all the moisture molecules in there, and they wiggle around and heat up the food. That's how microwaves work. But some older microwaves, if it's an older microwave where maybe the door is bent a little bit and it just doesn't seal up around it quite as good as it used to, a little bit of that RF activity, that radio frequency activity, can leak out, basically spewing out garbage all over the channel. And when that happens, our Wi-Fi devices are just basically going to throw up their hands and back off and wait for an opportunity to talk. Wi-Fi devices know that only one device can talk on a channel at a time, and that if something else is talking, they have to back off and be quiet. Now, this isn't just microwave ovens. This is cordless phones. This is analog video cameras. This is analog security systems. There are tons and tons of devices out there that operate in the 2.4 gigahertz band, and they have the potential to just spew garbage out onto our Wi-Fi channels, basically causing our Wi-Fi channels to back off and do nothing. Speaking of 2.4 gigahertz, I kind of want to make a quick comparison between these two because it's important to understand the differences between them. 2.4 gigahertz, as we all know, has a greater range. Most vendors are going to advertise about a 300-foot range. It's going to vary a little bit based on your environment, the building materials, even how many people are in the building can affect this, the antennas you're using, the client devices you're using, but most vendors are going to advertise about a 300-foot range. The 5 gigahertz band, on the other, has a much lower indoor range. It's only got a range of about 90 feet. Now, one question that you might have is why? Why is the range different? Well, it's because of the wavelengths. If we look at the 2.4 gigahertz wavelength, the actual wavelength is about 5 inches long. So if you look from the beginning of the wave to about the end of the wave, which is right about there, that's about a 5-inch span. That's about how long the 2.4 gigahertz wavelength is. Whereas the 5 gigahertz wavelength is much shorter. They're packed in much closer together. It's a higher frequency, so it's a shorter wavelength. The real length of a 5 gigahertz wavelength in inches is about 2.3 inches. Not nearly as long at all. And the result of that is that 5 gigahertz just doesn't do as good of a job of punching through stuff. It doesn't go through walls and doors and filing cabinets and desks and people nearly as well as 2.4 gigahertz does. So it has a much shorter indoor range. You put them outdoors side by side, it's almost the exact same thing. In fact, a lot of point-to-point links outdoors are often done in 5 gigahertz because it's really about the same when there's no obstructions in the way. Now, because of that shorter range thing, 2.4 gigahertz has always been more popular. So we see universal compatibility with 2.4 gigahertz. If you go out and buy a device that says it has Wi-Fi, it's going to support 2.4 gigahertz, no problem. You're definitely going to have that. Whereas 5 gigahertz support is a little more hit and miss. Now, this is getting better, but we still see quite a few devices out there that do not support the 5 gigahertz band. A few good examples are Motorola. Their Moto G and Moto E phones are both they're budget phones. You can pick up an unlocked Moto E on Amazon for about $100. Really, really inexpensive. Whereas their more premium phones like the Moto X and the Moto Z, those phones have a 5 gigahertz radio on board. So some devices, especially inexpensive Windows laptops, older iPhones like an iPhone 4S is not going to have a 5 gigahertz radio, so watch out for that. But there's still a few devices out there that don't support the 5 gigahertz band. Now 2.4, since it's always been more popular, is highly congested with Wi-Fi. There's a ton of Wi-Fi in 2.4, whereas 5 gigahertz is a lot more quiet in comparison. It's also plagued with non-Wi-Fi interference. The things we talked about earlier, the cordless phones, the wireless video cameras, the microwave ovens, the baby monitors. There's tons of stuff that operates there. And then there's my biggest beef with 2.4. My biggest problem with 2.4 is that we only have 3 channels to work with. 3 channels for us to use, whereas in the 5 gigahertz band, we have 24 channels to work with. And you remember how we talked about how only one device can talk on a channel at a time. That means that each channel has a limited amount of capacity available on that channel. There's only so much data we can cram through a channel before it's done. It's overloaded, just like a 2-lane highway or even a big 4-lane highway can get overloaded. In fact, the freeway on the way to work this morning was a crawl because 4 lanes of traffic in each direction, but it met its capacity. Channels are the exact same way, and 2.4 gigahertz has a lot more potential for a lot more throughput. Sorry, 5 gigahertz rather has a lot more potential for a lot more throughput because there's just a lot more channels available for us to use. Now, you might be thinking to yourself, hang on a second, Joel. You're telling me that there's only 3 channels in 2.4 gigahertz. I've set up a few access points and routers in my day. Pretty sure there's more than 3 to choose from. Where are you getting that number from? Well, it's because of how channels are laid out in the 2.4 gigahertz band. You're not wrong, but the channel layout in the 2.4 gigahertz band is a little funky. So let's go ahead and take a look at that. Each channel is 20 megahertz wide. That's the actual width of each wireless channel in the 2.4 gigahertz band. But if we look at the total width of 2.4 gigahertz, at least what we're allowed to use for Wi-Fi, it's really only about 60 megahertz wide. So you do some math, 60 divided by 20, you realize there's only enough room for 3 channels in 2.4 gigahertz. So how is it that we have 11 channels here in the United States to choose from? Well, it's because of how these channels are laid out. Each channel is marked by its center and each channel center is only separated by 5 megahertz. And so you put channel 1 and channel 2 side by side, and you visualize those, and you realize that they overlap by about 75%. In the end, the only 3 channels that do not overlap are channels 1, 6, and 11. Those are the only 3 channels that don't overlap. So the next question that you might have is, okay, good to know, but why does it matter if channels overlap? Well, it matters because of how Wi-Fi interferes with itself. There's 3 main types of interference in Wi-Fi. The first is co-channel interference. Co-channel interference occurs when we have a bunch of access points and client devices all on the same channel. And when they're all on the same channel, they all just take turns talking. Now, that works great as long as you don't have too many devices on the channel. Think of it as kind of like a dinner table. When you have a dinner table with only 4 people at the table, you guys have plenty of time to talk, right? Everybody gets to participate in the conversation, and everybody gets to participate and be involved in that somehow. But when you have a big dinner table with lots of people around the table, maybe you have 10, 15, 20 people around one dinner table, it gets really difficult to get a word in because there's a lot of people that want to talk. Wi-Fi is the exact same way. Co-channel interference is just fine. It's all good until you get too many devices on the channel and you reach the capacity of the channel. Then there's no time left for devices to talk. The next type of interference is adjacent channel interference. Adjacent channel interference happens when we have networks and client devices on partially overlapping channels. So let's say that we have a network on channel 5 and a network on channel 6 and a network on channel 7. Instead of politely taking turns talking, all of these networks and all their connected clients are just going to yell and scream over each other. I just accidentally unplugged my headphones, and so that really threw me off there. Got them plugged back in now, so we're good to go. Adjacent channel interference causes everyone to just yell and scream over each other. They interrupt each other constantly. It's kind of like all my daughters at my house. The oldest is 6, and so there's a lot of interrupting right now. They don't understand the difference between co and adjacent channel interference either. We want to avoid adjacent channel interference at all costs. We want to politely take turns talking. And when we use partially overlapping channels, that doesn't happen. It causes retransmissions, which causes more congestion on each channel, which slows each channel down. It's a wreck. So we want to avoid adjacent channel interference at all costs. The third type of interference is non-Wi-Fi interference. Non-Wi-Fi interference happens when a non-Wi-Fi device pops up on the same channel as our network and starts spewing out garbage all over it. Non-Wi-Fi devices don't have the same politeness mechanisms built in. They just show up on a channel and they just start talking. And when that happens, our Wi-Fi devices will just simply back off and be quiet and wait for their turn to talk. So how do we detect these different types of interference? Well, the classic way of doing this is with a Wi-Fi scanner. Wi-Fi scanners use a normal, typical, off-the-shelf Wi-Fi adapter to scan for wireless networks. And one innovation that MetaGeek came up with, this has been many years ago now, but this was us, I'm pretty proud of this, is we came up with this cool way of visualizing those wireless networks. We plot them out into this graph, and so you can see which channels they're on. For example, we can see that we have networks on channels 1, 6, and 11, and we've got a few extra networks right here on channel 11, and we've got some adjacent channel interferers here on channels 9 and 10. So that's a great way to visualize which networks might be causing interference. But the problem with Wi-Fi scanning is that there's a little bit of information that we miss here. Like, for example, how busy is channel 1? Really? I mean, is channel 1 being used 10% of the time? Is it being used 90% of the time? We don't know. We have no way of knowing how busy that channel actually is. And is there a non-Wi-Fi device on channel 6 causing interference? We don't know. The problem is that a Wi-Fi adapter can only tell us where the networks are. It's not able to show us everything that's happening, and so we miss a lot of that information, and that's where spectrum analysis comes in. A spectrum analyzer is a special piece of hardware that can hear all of the raw radio frequency activity in the spectrum. It's going to show us a couple of really important things. The first thing is it's going to show us interference from non-Wi-Fi devices, things like cordless phones, wireless video cameras, microwave ovens, baby monitors, all that stuff. We're going to be able to see all of the raw radio frequency activity, and so we can see anything that talks, including Wi-Fi, in the 2.4 and 5 gigahertz bands. It's also going to show us Wi-Fi channel congestion as well. we could see how often each channel is being used. If a channel is only being used 10% of the time, then we know there's a lot of capacity left on that channel. If it's being used 90% of the time, then we know that that channel is basically full. The next thing that we need to think about when we're deploying and troubleshooting a wireless network is channel planning. And channel planning in the 2.4 gigahertz band is really, really tricky. You remember how we talked about the nature of co-channel interference and how when we have too many devices on the same channel, we run out of opportunities to talk. Co-channel interference can help us minimize that as much as possible. So what we're going to do is, as we add access points to our network to cover new areas of the network, we are going to put new access points on a different channel. So if we start out here with channel 1, when we install our next access point, we're going to put it on channel 6. So that way, these two coverage cells that are made by these two access points don't have to take turns talking. They each have their own contention domain, their own spot where they can talk. And when we add another access point, we're going to go ahead and use channel 11. So we've used channels 1, 6, and 11, so they don't partially overlap, and we've put them all on different channels, so none of those coverage cells have to wait for each other to finish talking. They can all just talk amongst themselves. Okay, so we've deployed 3 access points now, but we are out of channels. We've run out of channels. So what do we do now? Now, we're going to go ahead and start reusing our channels. So the next access point that we're going to put in, we're going to go back to channel 1, and then we'll use channel 11, then we'll use channel 6 again. What you'll notice here is that we've kept our same channel coverage cells as far away from each other as possible to try to keep them from hearing each other. Now, in 2.4 gigahertz, that's going to be very hard to make them completely not able to hear each other. It's very, very difficult to do, but you can minimize it as much as possible. Now, in the 5 gigahertz band, channel reuse is a lot easier because we have 24 channels to work with. So it's just much easier. We don't actually have to reuse any channels until we've deployed 24 access points. So you'll notice that we've got one channel 36 here, and that's it. And then we can go to channel 52, and then channel 60, and so on and so forth. Channel planning in the 5 gigahertz band is a lot easier because of how many more channels that we have available. And I'm going to show you how to do channel planning with Insider Office. The next thing that we need to worry about is coverage. This is perhaps one of the most important things to have in Wi-Fi is coverage. And to get coverage, we have to understand a couple of things about signal strength. A couple of things that are really important. First off, we measure signal strength in dBm. Now, there's another measurement out there. We could measure it in milliwatts, but the really annoying thing about milliwatts is that a small change in signal strength in milliwatts can change the decimal place a ton. So, for example, one measurement that you might take might be 0.000001 milliwatts. And then when you go down in signal strength slightly, then you'll add a whole bunch of zeros to your milliwatts then. So it gets very, very annoying to try to calculate signal strength and monitor signal strength with milliwatts. So we use a measurement called dBm, that's decibels in relation to a milliwatt. This simplifies things a bit, but there are a couple of caveats here that we have to watch out for. The first thing to know about signal strength in dBm is that Wi-Fi is so weak, it's very, very quiet, extremely quiet. And so we actually are down in the negatives for dBm. So when we look at dBm, we are working in negatives. So negative 30 is a much higher signal strength than negative 90. That's the first thing to know. The second thing to know about signal strength is that this is not a linear scale. This is a log scale, which means a small change actually equals a big change in an exponential change as we go through our signal strength. So let's say that we're at negative 30 dBm and we drop down to negative 33 dBm. That just cut our signal strength in half. If we go down 3 more dB, down to negative 36 dB, we just cut our signal strength in half again. The same is true if we go in the opposite direction. If we're at negative 36 dBm and we go up to negative 33 dBm, we just doubled our signal strength. And if we go up to negative 30 dBm, we just doubled our signal strength again. That's called the rule of threes. We go down 3 dB, we cut our signal strength in half. We go up 3 dB, we double our signal strength. Okay, so now that we understand how signal strength works, let's take a look at some common signal strengths that you will kind of be able to watch out for. Now, these are just my opinions. Other engineers, they might have some slightly different opinions on where these should be. That's fine. That's okay. We don't have to agree exactly on this. This is just based on my personal experience, and other engineers out there, they're going to have a different experience. That's totally fine. In my experience, negative 30 dBm is basically the maximum achievable signal strength you can get. That basically means that you are 12 inches away from the access point. You're just super duper close. Doesn't necessarily mean it's good, it's not bad, it's just really, really high signal strength. Negative 67 dBm is what I consider to be the minimum for applications that require timely packet delivery. Think things like voice over IP or streaming video with Netflix or any kind of streaming service like that. When we're moving a whole bunch of data, we need to be able to transmit it the first time, have it reliably get there the first time, and then reliably get an acknowledgement back the first time. We don't want to be messing with any retransmissions or delivering packets out of order or anything like that. When that happens, that voice over IP call starts sounding like a robot, right? We've all experienced that, and that's because packets were not being delivered in a timely manner. So negative 67, that's my target for voice over IP. Now, if we go down 3 dB, remember, it doesn't look like a lot, but it is. We just cut our signal strength in half. We go down to negative 70 dBm. That's what I consider to be the minimum for reliable packet delivery. Think things like email and web. Sure, we're going to have to retry a few times in the background, but if we're just browsing Facebook, who cares? You know, the end user isn't going to notice any kind of performance problems at negative 70 dBm. Things should still be pretty reliable there, but maybe voice over IP might start to suffer a little bit. At negative 80 dBm, that's what I consider to be the minimum for basic connectivity. And at that point, things are probably going to be kind of unreliable. You'll notice that your actual throughput will go down. Your client devices might get grouchy and they might disassociate from the network. It's probably not going to work that well. At negative 90 dBm, that is basically approaching the noise floor. The background noise is overtaking the signal, and so things are not going to work well at that signal strength. The next thing that we need to worry about is security in wireless. When we are transmitting data back and forth between access points and client devices, we need to encrypt that data. If the data isn't encrypted, remember, most access points and client devices have omnidirectional antennas, so they broadcast in all directions. So it's very, very easy for an attacker to sit there and watch the data fly across the network. They can just simply eavesdrop on the conversation. And if you use a weak encryption standard like WEP can very, very easily be cracked and allowing an attacker to eavesdrop on that encrypted conversation because it's a weak form of encryption. So we need to be sure to use a good form of security like WPA or WPA2 to ensure that we don't run into any of these problems. So here's the different types of security that are out there. The first type is, well, no security at all. Open means no encryption at all, but it's good for guest networks because it allows people to get on and off of your network at will, which is great for things like coffee shops and hotels. WEP originally stood for Wired Equivalent Protection, which makes us laugh now because it's easily cracked with free tools such as AirCrack NG for Linux. Very, very easy to crack. A WEP network can be cracked in somewhere from 30 seconds to 5 minutes. Very, very easy to crack a network. WPS is another kind of an add-on for WPA that allows you to push buttons on the access point and push a button on your client device to synchronize them together and get them on the same network. It's easily brute forced with a tool called Reaver for Linux. And so again, that one is broken. We don't want to use WPS. WPA Personal was introduced as a stopgap for WEP. The Wi-Fi Alliance went, shoot, we have got to fix this WEP problem. So they introduced WPA Personal as a stopgap. So it's pretty okay security. It's good for older devices. But these days, you really probably won't have to use this anymore because everything out there now should support WPA2 Personal. WPA2 Personal is the final form. It's the final form of WPA. It's not the stopgap. It's the end goal. And so it's good for security in homes or small businesses, maybe a place with less than 10 users. The disadvantage with WPA Personal is that it uses a passphrase that everyone shares. So it's easy for that to get leaked out. You know, somebody, if that got leaked out of the business, well, then you've got a problem because now other people can get on the network. The best form of security is WPA2 Enterprise. With WPA2 Enterprise, everybody gets a unique username and password. And so when an employee leaves the company, you can simply delete their user account or disable their user account, and that's it. They can't get in anymore. And if somebody shares their password, well, you'll know about it because you'll see that suddenly that user has 20 devices on the network. So that's the best form of security, and it's great for larger larger organizations when you've got a big network. Okay, so now that we've covered all the basics, let's apply it. So let's use Insider Office. We're going to go through a few exercises here. We're going to avoid some non-Wi-Fi interference with it. We're going to measure and avoid some congested channels. We're going to use the channel planning in it to figure out how to plan all of our access point channels. We're going to check coverage. We're going to do security checks, and then we'll finish up by going through our network checklist. And I have also plugged in a WiSpy DBX to provide me with the spectrum analysis data that we need to see everything that's happening in the spectrum. Okay, so here we go. We've got Insider Office up and running here. So the very first thing that we're going to do is we can see our list of wireless networks here, and we can see those networks graphed out in both the 2.4 and 5 gigahertz networks, or networks graphs down here, so we can see what's going on. Now, the first thing that I'm going to do is I'm going to actually filter down to my network. And big surprise, my network here is called MetaGeek. I know, right? Nobody was expecting that. And so now we can see all of the access points that belong to the MetaGeek network. Now we've got a couple of different ways of grouping together all of our access points here at MetaGeek. The first way that we can group things together is by radio. Now we're not using virtual SSIDs here, but I'm sure you've all seen an environment where we were using virtual SSIDs. Maybe you would have, let's go find one really quick actually. Let's go find somebody that's using a virtual SSID. I know there's one here somewhere. Scroll down the list. There he is. Found him. So this particular network, or was I wrong? Did I click on the wrong one? Let's double check. I'd meant to write down the name of this one, but funny enough, the networks around our office, they actually tend to kind of come and go quite a bit as businesses move around and businesses change. He must be just out of range where I just can't see him today. But what we would get here is under the SSIDs column, we would get multiple SSIDs listed under one radio. So what we do with this tool is we group together multiple SSIDs that are being broadcast from the same radio. The advantage of a virtual SSID is you can have several different networks provided by one access point. So for example, we could have MetaGeek and then we could have MetaGeek Guest, both being broadcast from the same access point radio. And we would group those together here. So when we select this, you'll notice that it gets colored in blue down here at the bottom. So here's the SSID. It's MetaGeek Lab TP-Link is the name of the network. We can see we're using WPA2 Personal, and we're currently on channel 6. We can see that there are currently, we've got about 16 networks that are sharing the same channel. And notice that we've got this in this yellow section here. We're also coloring them in yellow down here in the bottom too. And we're also coloring them yellow over here in the list so you can see exactly who is causing co-channel interference with your network. Now, the next thing you'll notice is that there are two networks that are partially overlapping. In fact, I've got another network that's even a better example here. This guy, BBA. I really like BBA because he's on a terrible channel. He's on a really, really bad channel. You'll notice that he is overlapping with 25 other access points, and all those access points are colored in red. So we can see exactly who those are. We can see them over here. And so this is a bad channel. We are not on a good channel right now with this network. And we're going to come back to that in just a minute. So physical mode looks at each individual radio. Logical mode, this button up here, logical mode, does something a bit different. It groups together networks by name. So it'll actually group together all of the access point radios that have the same name. So for example, if we click on MetaGeek, we're actually going to select every single MetaGeek access point radio that we can hear from here, which is 4. We've got 2 down here in the 2.4 gigahertz band and 2 of them up here in the 5 gigahertz band. So that's the difference between logical mode and physical mode. Logical mode groups together all the APs with the same name, and physical mode looks at one access point, but it groups together multiple virtual SSIDs. So the first thing I want to do is let's skip over to the channels view, and this view is going to show us the raw radio frequency activity from the WiSpy, from the spectrum analyzer. So we can see a couple of things. Down here, you'll notice that we've hidden all of the networks so we can see the spectrum data. The color here tells us how often things are talking. So if you see blue, that means that something talked there, but it didn't talk for very long. But then as you get up to red, red indicates that something was talking there a lot. Something was talking a lot. We can also see on a percentage basis how often each channel is being used with the channel utilization column. For example, if we look at channel 6, we can tell it's being used about 16% of the time. So now what we're going to do is let's create some non-Wi-Fi interference. It's a good thing I'm not giving this webinar over Wi-Fi right now because I'm going to blow it up pretty bad. So we're going to turn on a non-Wi-Fi device. It's this is very similar to a cordless phone. A cordless phone makes a very similar shape in the spectrum. So now if we look down here on channel 1, we can see that there is a shape popping up right there, and that is the shape of a cordless phone. On top of that, if we look at our utilization up on channel 1, you'll notice that channel 1's utilization is going up and up and up. Right now we're seeing about 50% utilization, but I would say that we're going to top out at around 70% utilization because this device, whatever it is, talks constantly, and so it's not going to allow any Wi-Fi devices on that channel to transmit. So now let's go ahead and unplug that for a minute. Now that we know it's there, but I want to show you how we make channel recommendations in the software and how Insider Office can help you avoid interference. So let's go find somebody on channel 1. So I'm just going to sort this by channel. So we'll put the lowest channels up at the top here. Let's click on Iris. Let's check out Iris and see what's going on with Iris. So right now we're on channel 1 and we're recommending channel 1. But if we plug in this non-Wi-Fi interferer and give it a moment, what you'll notice is that our channel recommendation after this device has been running for a few minutes will actually change. We'll say, okay, statistically this was a good channel, but it's not a good channel anymore. This is now a bad channel. So what you'll notice is that now we've actually got a new recommendation. We're now recommending that you move to channel 6 to get away from that non-Wi-Fi interference. So Insider Office will automatically help you pick a better channel for your wireless network to get away from non-Wi-Fi interference. The next thing that we want to do is we want to be able to see Wi-Fi congestion as well, and that is represented much in the same way. If we go back to the channels view here, oh no, Insider crashed. One thing, it's crashing bad too. Hang on a second, let me get this fixed. There is a couple features in here that are in, this is an internal beta version, not even an external beta. There's a couple features in here I wanted to show you and give you a sneak peek of. So not surprised to see that it crashed. And now our developers, they should have received a notification that it crashed, so they can go ahead and get that fixed before we release it. So sorry about that. Okay, Insider Office is starting back up. It's not a bug, it's a feature, right? So now what I'm going to do is let's create some Wi-Fi congestion. So what I'm going to do is I'm actually going to filter down to a specific network here. It's called MetaGeek Lab TP-Link. So this is a little access point that I've got out in the hallway here, and I've got a throughput testing server hooked up to it. So what I'm going to do now is I'm going to get out my tablet. I've got my old 2013 Nexus 7 here. I love this tablet. Never going to let this thing go. And I'm going to start up, let's let it connect to the Wi-Fi, and I'm going to start up a throughput test on it. Now watch down here where MetaGeek Lab TP-Link is. What you're going to notice is that there's going to be this flat tabletop shape that emerges around that network. That is activity from our throughput test. If we go over to the channels view, we can see very clearly that flat tabletop shape. That is the activity of the throughput test between my tablet and the throughput testing server. And we can see that channel 6 is being used about 46% of the time. We're actually keeping that channel pretty busy. So you can measure channel congestion by looking at the utilization of a specific channel, and you can even correlate which network it belongs to by just looking to see if it lines up with the same channel as a wireless network, as well as the same height, the same loudness. And these will be factored into our channel recommendations as well. If we were to go look at this network, we can see that it's on channel 6 right now, but because of that congestion, we're going to go ahead and recommend channel 1 to get you to a less congested channel. So it can help you see how busy each channel is. The next thing that we can do with this tool is channel planning with this recommended channel feature. So what we can do is we'll get rid of our we're going to get rid of our filter here. So we're going to show everybody, and then I'm going to bring in the MetaGeek filter here. MetaGeek. We're not Greek. Let's see if I can type here. There we go. I'm trying to type around my microphone. It gets a bit tricky sometimes. So now if we go over to logical mode and we select our wireless network, we can see which channels all of our individual access points are on. So what I'm going to do is I'm going to go back to physical mode, and I'm going to look at each one of our access points, like the plank and the front desk, and this one I'm not sure where it is, so I've actually labeled it with question marks. I've got to figure out which one that is. I think I think it's also the one by the front desk, but I need to walk over there and see if the signal strength goes up to confirm that. So what we can do with these is we can look at our recommended channel. We can go stand next to our first access point and look at the recommended channel and see what it is, and then configure it for that channel. Then we walk to the next access point and stand next to it and look at the recommended channel and configure that. Insider Office should just evenly distribute them on channels 1, 611, 1, 611, 1, 611 as you move through the building. The same goes for 5 gigahertz channels as well. We will look at things in the 5 gigahertz band, and we'll make channel recommendations there as well to help you figure out which channel all of your access points are on. So the process is stand next to the access point, select the radio. If you sort it by signal strength, it should be the top of the list. So we'll sort these by signal strength. Remember, lower number is actually higher because we're working in negative, so we stand next to the plank, which is what we've named this access point, and we can look at that recommended channel and know which channel it should be on. And you do that for every access point, and you have effectively planned out everything for your network. The next thing you might need to do is check for coverage. If you go to logical mode and select your network, you're going to get a signal strength graph for each one of your access point radios. So you can see where the colors are each tied to a specific signal strength line here. The next thing you can see is we have a signal strength threshold. So if you decide what signal strength you want to achieve on your network, you can set a threshold. And then you can simply walk around and make sure that your signal strength lines stay above the threshold. If they go below the threshold, then you'll notice that the signal lines or the signal numbers here will actually turn red if they're too far away. As long as you've got one radio above that line at all times, you've got coverage. That's all you need to do is make sure you've got one line above the dotted line at all times. So how do we set this? How do we set our threshold? Well, if you go to settings and go to signal threshold, right now I've got it set to -80 dBm, but I'd really like to be able to support voice over IP here, so I'm going to switch it to -67 dBm. And you'll notice that our line moved up, and one of them, our question mark one, is actually every now and then falling below the line, so we can see whether we're getting coverage from that AP or not. You can also change the amount of time that we're putting in here. Right now I have it set to 30 seconds, but I'm going to go ahead and boost this up to 5 minutes, and that's going to give me a much more historical look at what's going on, so I can really track over time what is happening. The last thing that you can do with this is that I want to talk about is perform a security check. If you go find your network on this list, and I'm actually going to just filter down to BBA. Remember BBA? I used him as an example earlier. Ooh, he's gone. Let's find somebody else. I'm going to go to physical mode and track somebody down. Oh no, it crashed again. Ooh, this will teach me to run beta versions. Usually these betas are pretty solid, but ooh, this is a little bit. This is an interesting one. I think I know how to reproduce the crash now, so I'll go talk to developers about that. We're probably going to release this version in a week or two. So there's a couple nice new features in here. The one that I wanted to show you was the pin network feature, which I'm pretty excited about. You can now pin your network to the top. I'll show you that really quick. If you go to logical mode and let's filter down to MetaGeek. And by the way, we'll automatically pin a network if you're connected to it. So you can even usually skip that step. You can hit this pin button here, and now that network is pinned, so you can more easily keep track of that network. I wanted to show you the security feature in here, though. If you go and select your wireless network, we'll actually give you an alert if you've got poor security on it. This particular network, it's actually a hidden network, but we can see it because hidden networks don't add any security whatsoever, is using WEP. And as you can see, we've got a broken lock icon there, and we've also got an alert up here that says there's a security warning. WEP is enabled, which is a security risk, and you can even click Learn More to go find out a little bit more about that and why it's a security risk. So that's the other thing that I wanted to show you in the software. Okay, so let's go through our checklist. What do we need to do to make sure that our network is good to go? The first thing we need to do is let's use strong security. Let's use either WPA2 Personal or WPA2 Enterprise, and you're going to use either the security column to see those broken lock icons, or you're going to look at the alerts to make sure that you've got solid security. The next thing that we need to do is perform good channel selection. First off, we're going to avoid adjacent channel interference by using the recommended channel feature. We're also going to avoid Wi-Fi congestion and non-Wi-Fi interference by making sure that we've got a Wi-Fi Mini, that's our 2.4 gigahertz only Wi-Fi, or a Wi-Fi DBX, that's our dual band, both 2.4 and 5 gigahertz Wi-Fi plugged in. And then we're going to use the recommended channel feature to effectively reuse our channels and avoid co-channel interference with our own network. Next, we're going to allow devices to make roaming decisions by giving each AP the same SSID. And if we see them all grouped together in logical grouping mode, then we know that they all have the same SSID. And so we know that our devices are going to be able to make roaming decisions and move from access point to access point. We're also going to be sure to use the same security settings and passphrases to ensure that our devices will be able to roam from AP to AP. And we will show an alert if you are using different security types on your APs. We'll show an alert to let you know, hey, these are not using the same security type, and that's going to cause roaming problems. We're also going to plan for good coverage by picking a threshold, making sure that we've got a requirement, and then ensuring the requirement is met by walking around and looking at the signal strength threshold as well as the signal strength graph to see exactly what our coverage looks like on the network. Okay, and that's the content that we had for today. I'd like to open it up for questions. If you have any questions, please feel free to use the question tool. Go ahead and type those questions in, and we'll answer those. And at this point, I'll hand it back over to Julie.
Joel, thank you very much for your wonderful presentation. And it looks like I've got some questions here for you, so I'm going to read them off to you one at a time. Let's see, I'm going to start off with this first one here. Question says, will the spectrum analyzer pick up things like cellular boosters?
Ooh, that's a good question. So cellular technologies, those are licensed technologies, which mean they work in licensed spectrum, meaning, for example, AT&T will purchase a license to operate their stuff in a completely different slice of spectrum. The 2.4 and 5 gigahertz bands are unlicensed, which means you don't have to have a license to operate stuff there. As long as you follow some certain rules. Most cellular boosters are going to operate in completely different frequency bands. They're going to operate in around 850 megahertz, 950-ish megahertz. I think there's some stuff up in 2.1 gigahertz, but they're different frequency bands. So typically, cellular boosters are not going to interfere with the 2.4 and 5 gigahertz bands. But unfortunately, this is not a short answer. But some cellular boosters and even some cell towers can cause what's called out-of-band interference, where they will cause the noise floor in the 2.4 or the 5 gigahertz bands to go up. And the Wi-Spy will show a heightened noise floor. You can check out our knowledge base, look for noise floor in our knowledge base, and there's a good article there about that. Another thing to consider is that LTEU, you may have heard of LTEU. To my annoyance, some cell carriers are calling that 5G. I don't like that because people confuse that with 5 gigahertz. LTEU is going to operate in the 5 gigahertz band, which can completely knock out a couple of channels for Wi-Fi, and the Wi-Fi DBX will absolutely pick that up.
Joel, thank you very much for that. I'm going to go on to the next question here. Do you have anything for the 900 megahertz reel?
Ooh, good question. We don't have anything in 900 megahertz right now. We used to have a product called the Wi-Spy 900X. I have one, and I'm very closely guarding it because I only have one left. Unfortunately, we had to discontinue it because there was a lack of interest in the product. We just weren't selling very many. So, in fact, when we discontinued, it took a long time to sell out our existing supply. But that was many years ago now. Unfortunately, we don't make it anymore.
Thank you very much for that. Let's see, next question. Are there options for samples to test or any way to see how this all actually works before buying?
That's a great question. If you contact our support team, we can probably get you a license key for Insider Office. Insider Office will work without a Wi-Spy. You just won't get any spectrum data. You'll only get the Wi-Fi scanning data. So, for example, the channels tab that I showed you will be disabled, and then the channel recommendations, they won't factor in any Wi-Spy data because it's just not there. So contact our support team, support.metageek.net, or email us at support@metageek.net. We'd be happy to get you a trial key so you can test it out.
Thank you very much. Next question. In regards to channel interference, Does it recommend a channel for both 2.4 and 5 gigahertz channels?
Yes, it does. So each access point, a dual band access point is really more like two access points that are enclosed in one box. One access point's in 2.4, one access point's in 5 gigahertz. In fact, client devices see them as two separate access points, the 2.4 and the 5. In Insider Office, we list each radio individually, so you can click on the 2.4 gigahertz radio and get your recommendation for that radio, and then you can go click on the 5 gigahertz radio and get the recommendation for that radio as well. So two separate channels because they're on two separate frequency bands.
Thank you very much. Got a next question here for you. Is MetaGeek running any shows or events that we can send a sales rep to?
That's a good question. We're not really hosting any events right now, but we're definitely considering that. If you're interested, go ahead and get in touch with me. My email address is joel@metageek.net. Just shoot me an email, joel@metageek.net. I'd be more than happy to discuss that with you. We're not running anything right now, but it'd be great to get your feedback and see exactly what you're looking for.
Thank you very much, Joel. I've got several comments here saying thank you for such an informative webinar. Everyone enjoyed it very, very much. And I'd like to thank you very much for answering all those questions and to thank everyone for attending today. And if anyone wants to contact us regarding any of the items that you've seen here, please email us at sales@microcomtech.com. And if anyone wishes to review the products mentioned or shown today, please visit us at www.microcom.us. And please remember, this webinar presentation is being recorded and it will be uploaded to our YouTube channel. So to reference this again and view it again, it will be on YouTube. Thank you very much. Thank you, Joel, so much for your time and your presentation today. We very much appreciated it and enjoyed it. And everyone have a terrific day.